So hello and welcome back to this online machine learning course. So in the last video, we dealt about gradient descent. We saw the mathematical derivations, as you can see over here. We saw this mathematical derivation where this is the gradient, and we look at the graphical intuition about how we actually descend from this point to this minima over here, and we saw the best fit curve. From this curve or this curve we choose how it actually converges to this graph and lots more. Now in this video we'll be dealing with gradient descent more formally, and we will be dealing more aspects of gradient descent. So gradient descent formally can be defined as an optimization algorithm used to minimize some function by iteratively moving in the direction of steepest descent and defined by the negative of the gradient. Okay, so in this scenario discussed before, our optimization algorithm is this mean squared error, where this y hat is given by this expression, right? We have dealt about it in great detail, so you must be knowing about it. Now, it is an optimization algorithm used to minimize this function. It is used to minimize in this function in our case. Now, this mean squared error may change in further videos, but the main point is to minimize some function by changing these b0, b1 to bn. Let's look at further examples. So let's for the time being assume that this is my error surface and this is my error axis, and this is perhaps the first weight axis and this is perhaps the second weight axis, right? So you can find out that this is the point of maximum error, and this let me take a different color, this perhaps is the point of minimum error, right? This one. So our objective is to move from this point to this point. Now physically, if I tell you this problem, you would be moving downwards, and more appropriately you would be moving in this path, right? So in gradient descent we move along the derivative of these two weights. So the derivative is nothing but d error by dw1 and d error by dw2. So we change our weights, I mean w1 is changed to a value of w1, the old w1, minus some value eta into the dE by dw1, right? Similarly for w2 and similarly for all the values. We do this iteratively. We perform this operation iteratively until we reach this position. Like, let's for example consider this situation. Here for example, this is my error surface, this is my error axis, this is my weight 1 axis, and this is my weight 2 axis. Now initially I've chosen my weight w1 and w2 such that my error is in this point, and I want to minimize this error. So basically what I will be doing is that I will be moving along the points where my error is minimized. So let's consider in this point the derivative in this case would be with respect to w1, or this quantity would be somewhat like this. With respect to w2 it would be somewhat like this, And so our path or our point would be moving in somewhat this direction, the resultant of this, right? In this iterative manner, let's consider it moves in this direction and it moves in this direction. The resultant would be in this direction. And so similarly, we after several iteration might reach up to this point and perhaps over this point, whichever point it is. And so yeah, that is the way how we actually make our predictions. And let's move on further. Okay. So initially, you would see that we have the red point over here. And now we want to somehow reach this position where our error is minimized, right? So now in these areas, probably in these areas, your derivative or dE by d del w1 I could be equal to 1 or 2, right? This is a very large quantity, right? So it would, so w1 wi minus del E by del wi would be a very large quantity, right? So there would be a large change in this graph, in this quantity from w1, right? So this would actually take large steps, right? So initially it would be here, finally it would be here, somewhere here, it would be here, then it would be perhaps be here, then it would perhaps be here, and as we would be moving down. When this quantity is actually getting small, it would take smaller steps, and in this region where the derivative is supposedly getting small, our graph would be actually moving somewhat like this, and then it would finally converge. So you can see there are large gaps over here, large gaps, and then very small gaps and minuscule gaps in this final areas. So yeah, that is how we actually move to our correct graph. And if you see, this is the wrong graph in this case, and the correct would be actually this graph, which approximately classifies the, I'm sorry, not classifies, approximately predicts my correct output. Now, okay, so this is what was linear regression. Now suppose my output function, I want to predict about multilinear or I'm sorry, bilinear or these graphs, because let's take for this example. Now in this case, if you apply only a simple linear function, for example mx plus c, you would be getting somewhat this graph, right? But you are not exactly predicting, because for these points you are having a large errors. Like for these points and for these points, you are having large errors. So, and there might be situations where a linear graph may not always be the best choice. A non-linear graph or a quadratic or a bicubic graph or other graphs, for example x squared or x cubed or x to the power n, may be the correct choice. As you can see over here, this could be this graph or this graph or this graph. So how do we accommodate this? Well, it's not very difficult. We can just extend our idea of linear regression. So for the time being, we know that y is equal to this, right? And we know mean square error is nothing but y minus y hat. And suppose if I somehow I want this squared, so what I can do is that I can add b n plus 1 x1 squared, right? And this x1 squared could be another table, right? For example, let me take this indus 1, and this indus squared could be actually like indus squared, or for the time being let me take this radix squared. Okay, so radix squared could contain the values of perhaps 1, 4, 4, 9, 9 and so on. So you can see you are forming a new table, a new feature, and you are actually squaring this part and forming it a new feature. And you can extend this idea to n linear examples as well. And so that is how we actually deal for x squared or x cube, and this is how we actually accommodate this graph. This is how we actually get this graph, because we actually form the squared one and treat this as a feature, for example y eta I'm sorry, some feature new, right? We treat this as some feature new or some feature xn plus 1. This forms our new feature, and for example x1 cube could be our another new feature, for example n plus 2. And so this is how we extend our idea to non-linear regression as well. So yeah, that was for today, and thank you for watching.